Well, all right, I will get started then. Oh, by the way, this presentation will be posted to staffeng.careers. So please, encourage you to sign up there. It's a community of folks who are interested in growing to become software engineers. So a lot of really great learning there. And if you're not with Taro, I encourage you to join using my referral link, jointaro.com/alexpoon. You will get a discount, and I will also get a little bit of money as well too. Awesome. All right, let's get started. So what is Cassandra? It's an open source Apache project originally developed at Facebook in 2007 for the inbox search feature. Cassandra is designed to provide scalability, availability, and reliability to store large amounts of data. Cassandra combines the distributed nature of Amazon's Dynamo, which some of you may have learned about from our previous session, which is a key value store, and the data model of Google's Big Table, which is a column-based data store. With Cassandra's decentralized architecture, there is no single point of failure in its cluster, and its performance can scale linearly with the addition of nodes. So, what is Cassandra? It's decentralized, scalable, highly available NoSQL database. It's classified as an AP and a CAP theorem, meaning available and partition tolerant, which means that availability and partition tolerance are generally considered more important than a consistency. Cassandra can be tuned with replication factor and consistency levels to meet strong consistency requirements, but this comes with a performance cost. In other words, data can be highly available with low consistency guarantees, or it can be highly consistent with lower availability. Cassandra uses a peer-to-peer architecture with each node connected to all other nodes. Each Cassandra node performs all database operations and can serve client requests without the need for any leader node. We're going to try to be Cassandra version agnostic throughout this presentation and try to explore the general design and architectural layout of different Cassandra components and operations. By default, Cassandra is not strongly consistent. Hence, any application where consistency is not a concern can utilize Cassandra. Though Cassandra can support strong consistency, it comes with a performance impact. Cassandra is optimized for high throughput and faster writes and can be used for collecting big data for performing real-time analysis. Here are some of the top use cases of Cassandra. Storing key value data with high availability. Reddit and Dig use Cassandra as a persistent store for their data. Cassandra's ability to scale linearly without any downtime makes it very suitable for their growth needs. Also suitable for time series data model. Due to this data model and log structured storage engine, Cassandra benefits from high-performing write operations. This makes Cassandra well-suited for storing and analyzing sequentially captured metrics, such as metrics from sensors, application logs. Such usages take advantage of the fact that columns in a row are determined by the application, not a predefined schema. Each row in a table can contain a different number of columns, and there is no requirement for the column names to match. Write-heavy applications. Cassandra is especially suited for write-intensive applications such as time series streaming services, sensors, logs, and Internet of Things applications. All right, so let's go through the common terms of Cassandra. A column is a key value pair and is the most basic unit of data structure. The column key uniquely identifies a column in a row, and a column value stores one value or a collection of values. A row is a container for columns referenced by primary key. Cassandra does not store a column that has a no value. This saves a lot of space. What are the components of a Cassandra row? Key space, Key space is a container for tables that span over one or more Cassandra nodes. Cluster is a container of key spaces called a container of key spaces is called a cluster. Node refers to a computer system running an instance of Cassandra. A node can be a physical host, a machine instance in a cloud, or even a Docker container. NoSQL. Cassandra is a NoSQL database, which means we cannot have joins between tables. There are no foreign keys, and while querying, we cannot add any column in the where clause other than a primary key. These constraints should be kept in mind before deciding to use Cassandra. The primary key uniquely identifies each row of a table. In Cassandra, a primary key has two parts. The partition key decides which node stores the data, and a clustering key decides how the data is stored within a node. Let's take the example of a table with a primary key, city ID, employee ID. This primary key has two parts represented by the two columns. A city ID is the partition key. This means that the data will be partitioned by the city ID field. That is, all rows within the same city ID will reside on the same node. Employee ID is a clustering key. This means that within each node, the data is stored in sorted order according to the employee ID column. As we saw above, clustering keys define how the data is stored within a node. We can have multiple clustering keys. All columns listed after the partition key are called clustering columns. Clustering columns specify the order that the data is arranged on a node. As you can see on a node, data is ordered by the clustering key. Partitioner. Partitioner is the component responsible for determining how data is distributed on a consistent hash ring. When Cassandra inserts some data into a cluster, the partitioner performs the first step, which is to apply a hashing algorithm to the partition key. The output of this hashing algorithm determines which range the data lies and hence on which node the data will be stored. How do we distribute data on the consistent hashing ring? Well, by default, Cassandra uses the mir3 hashing function. Mir3 will always produce the same hash for a given partition key. This means that we can always find a node where a specific row is stored. Cassandra does allow custom hashing functions. However, once a cluster is initialized with a particular partitioner, it cannot be changed later. In Cassandra's default configuration, a token is a 64-bit integer. All Cassandra nodes learn about the token assignments of other nodes through gossip. We'll talk about this more later. Some of you may remember we discussed the gossip protocol in last week's in-depth dive into DynamoDB. This means any node can handle a request for any other node's range. The node receiving the request is called the coordinator, and any node can act in this role. If a key does not belong to the coordinator's range, it forwards the request to the replicas responsible for that range. A client may connect to any node in a cluster to initiate a read or write query. This node is known as the coordinator node. The coordinator identifies the nodes responsible for the data and is being written or read and forwards their queries to them. Let's talk about replication in Cassandra. Each node in Cassandra serves as a replica for a different range of data. Cassandra stores multiple copies of data and spreads them across various replicas so that if one node is down, other replicas can respond to queries for that range of data. This process of replicating the data onto different nodes depends upon two factors: the replication factor and the replication strategy. Replication factor. The replication factor is the number of nodes that will receive the copy of the same data. This means if a cluster has a replication factor of 3, each row will be stored on 3 different nodes. Each key space in Cassandra can have a different replication factor. The node that owns the range in which the hash of the partition key falls will be the first replica. All the additional replicas are placed on the consecutive nodes. Cassandra places the subsequent replicas on the next node in a clockwise manner. There's two replications in Cassandra. The first one you see in a slide here, it's called a simple replication strategy. This strategy is used only for a single data center cluster. Under this strategy, Cassandra places the first replica on a node determined by the partitioner and the subsequent replicas on the next node in a clockwise manner. The next strategy is called the network topology strategy. This strategy is used for multiple data centers. Under this strategy, we can specify different replication factors for different data centers. This enables us to specify how many replicas will be placed in each data center. Additional replicas in the same data center are placed by walking the ring clockwise, as you can see in this diagram here, until reaching the first node in another rack. This is done to guard against a complete rack failure, as nodes in the same rack or similar physical grouping tend to fail together due to power, cooling, or network issues. Does this make sense so far? Okay, we have some thumbs up. Awesome. Making sure everyone's still with us. It's great seeing some thumbs up. Cool. Let me know if I'm going too fast and you want me to slow down or anything like that. Cool. What are the consistency levels for Cassandra? Thank you for the feedback, by the way. If you want to give emotes along the way, that's also awesome feedback. Just give a thumbs down if you want me to slow down, and I'll listen to that. What are the consistency levels for Cassandra? Cassandra's consistency level is defined as the minimum number of Cassandra nodes that must fulfill a read or write operation before the operation can be considered successful. Cassandra allows us to specify different consistency levels for read or write operations. Also, Cassandra has tunable consistency, i.e., we can decrease the consistency levels for each request. There is always a trade-off between consistency and performance. A higher consistency level means that more nodes need to respond to a read or write query, giving the user more assurance that the values present on each replica are the same. Write consistency levels. For write operations, the consistency level specifies how many replica nodes must respond for the write to be reported as successful to the client. The consistency level is specified per query by the client. Because Cassandra is eventually consistent, updates to other replica nodes may continue in the background. Here are different write consistency levels that Cassandra offers. 1 or 2 or 3. The data must be written to at least the specified number of replica nodes before a write is considered successful. Quorum. The data must be written to at least a quorum majority of replica nodes, as defined in, as you can see here, the replication factor divided by 2 plus 1. For example, in a cluster with a replication factor of 5, if 3 nodes return success, the write is considered successful. The next level is all. This ensures that the data is written to all replica nodes. This consistency level provides the highest consistency but lowest availability, as writes will fail if any replica is down. The next level is local quorum. This ensures the data is written to a quorum of nodes in the same data center as the coordinator. It does not wait for the response from the other data centers. Each quorum. This level ensures that the data is written to a quorum of nodes in each data center. And the last level is the any. The data must be written to at least one node. In the extreme case, when all replica nodes for the given partition key are down, the write can still succeed after a hinted handoff. We'll talk more about this later. After a hinted handoff has been written, any consistency level provides the lowest latency and highest availability. However, it comes with the lowest consistency. If all replica nodes are down at write time and any write is not readable until the replica nodes for that partition have recovered and the latest data is written on them. How does Cassandra perform a write operation? For a write, the coordinator node contacts all replicas as determined by the replication factor and considers the write successful when a number of replicas equal to the consistency level acknowledge the write. Earlier, I mentioned hinted handoff. If you remember during the previous session last week, we also discussed hinted handoff in context of DynamoDB. Depending on the consistency level, Cassandra can still serve write requests even when nodes are down. For example, if we have the replication factor of 3 and the client is writing with a quorum consistency level, this means that if one of the nodes is down, Cassandra can still write on the remaining 2 nodes to fulfill the consistency level, hence making the write successful. Now let's talk about the hinted handoff. Now, when the node which is down comes online again, how should we write to it? Cassandra accomplishes this through hinted handoff. When a node is down or does not respond to a write request, the coordinator node writes a hint in a text file on the local disk. This hint contains the data along with information about which node the data belongs to. When the coordinator node discovers from the gossiper, which we'll talk more about later, that a node for which it holds hints has recovered, it forwards the write request for each hint to the target. Furthermore, each node every 10 minutes checks to see if the failing node for which it is holding any hints has recovered. Does that make sense so far? With a consistency level any, if all replica nodes are down, the coordinator node will write the hints for all the nodes and report success to the client. However, this data will not reappear in any subsequent reads until one of the replica nodes comes back online and the coordinator node successfully forwards the write request to it. This is assuming that the coordinator node is up when the replica node comes back. This also means that we can lose our data if the coordinator node dies and never comes back. For this reason, we should avoid using the any consistency level. If a node is offline for some time, the hints can build up considerably on other nodes. Now, when the failed node comes back online, other nodes tend to flood that node with write requests. This can cause issues on a node as it is already trying to come back after a failure. To address this problem, Cassandra limits the storage of hints to a configurable time window. It is also possible to disable hinted handoff entirely. Cassandra, by default, stores hints for 3 hours. After 3 hours, older hints will be removed, which means if now the failed node recovers, it will have stale data. Cassandra can fix the stale data while serving a read request. Cassandra can issue a read repair. Excuse me. Cassandra can issue a read repair when it sees stale data. We'll go through this while discussing the read path. Last, there's one thing to remember. When the cluster cannot meet the consistency level specified by the client, Cassandra fails the write request and does not store a hint. The consistency level for read queries specifies how many replica nodes must respond to a read request before returning the data. For example, for a read request with a consistency level of quorum and replication factor of 3, the coordinator waits for successful replies from at least 2 nodes. Cassandra has the same consistency level for read operations as that of write operations, except for each quorum, because it's very expensive. To achieve strong consistency in Cassandra, it gives us strong consistency. In the equation you can see on the slide, we get the read replica count, the write replica count, and a replication factor, respectively. All client reads will see the most recent write in this scenario, and we will have strong consistency. Next, we'll talk about the snitch. The snitch is an application that determines the proximity of nodes within the ring and also tells which nodes are faster. Cassandra nodes use this information to route read and write requests effectively. We'll talk about this more in detail later. I see a question about the coordinator node and a hint. So hints are stored locally on the coordinator node that generated the original write operation. So if server 6 generates a hint, the hint is stored in server 6 itself. If the coordinator node server 6 goes down before it can forward the hint would not be accessible until the coordinator node recovers. Okay. How does Cassandra perform a read operation? The coordinator always sends the read request to the fastest node. For example, for quorum equal 2, the coordinator sends the request to the fastest node and a digest of the data from the second fastest node. The digest is a checksum of the data and is used to save network bandwidth. If the digest does not match, it means some replicas do not have the latest version of the data. In this case, the coordinator reads the data from all the replicas to determine the latest data. The coordinator then returns the latest data to the client and initiates a read repair request. The read repair operation pushes the newer version of data to nodes with the older version. While discussing Cassandra's write path, we saw that the nodes could become out of sync due to network issues, node failures, corrupted disk, etc. The read repair operation helps node to resync with the latest data. Read operation is also used as an opportunity to repair inconsistent data across replicas. The latest write timestamp is used as a marker for the correct version of data. The read repair operation is performed only in a portion of the total reads to avoid performance degradation. Read repairs are opportunistic operations and not a primary operation for anti-entropy. Read repair chance. When the read consistency level is less than all, Cassandra performs a read repair probabilistically. By default, Cassandra tries to repair read Cassandra tries to read repair 10% of all requests with DC local read repair. In this case, Cassandra immediately sends a response when a consistency level is met and performs the read repair asynchronously in the background. Snitch. Earlier, I had mentioned the snitch. Snitch keeps track of the network topology of Cassandra's nodes. It determines which data centers and racks nodes belong to. Cassandra uses this information to route requests efficiently. Here are the two main functions of a snitch in Cassandra. Snitch determines the proximity of nodes within the ring and also monitors the read latencies to avoid reading from nodes that have slowed down. Each node in Cassandra uses this information to route requests efficiently. Cassandra's replication strategy uses the information provided by the snitch to spread the replicas across the cluster intelligently. Cassandra will do its best by not having more than one replica on the same rack. To understand Snitch's role, let's take the example of Cassandra's read operation. Let's assume that the client is performing a read with quorum consistency level and the data is replicated on 5 nodes. To support maximum read, Cassandra selects a single replica to query for the full object and asks for the digest of the data from 2 additional nodes in order to ensure the latest version of the data is returned. The snitch helps to identify the fastest replica, and Cassandra asks the replica for the full object. Gossip protocol. Cassandra uses Gossip protocol that allows each node to keep track of state information about the other nodes in the cluster. Nodes share state information with each other to stay in sync. Gossip protocol is a peer-to-peer communication mechanism in which nodes periodically exchange state information about themselves and other nodes they know about. Each node initiates a gossip round every second to exchange state information about themselves and other nodes with 1 to 3 other random nodes. This way, all nodes quickly learn about all other nodes in a cluster. Each gossip message has a version associated with it, so that during a gossip exchange, older information is overwritten with the most current state for a particular node. Generation number. In Cassandra, each node stores a generation number which is incremented every time a node restarts. This generation number is included in each gossip message exchanged between nodes and is used to distinguish the current state of a node from its state before a restart. The node receiving the gossip message can compare the generation number it knows and the gossip message's generation number. If the generation number in the gossip message is higher, it knows that the node was restarted. Let's talk about seed nodes. To prevent problems in gossip communications, Cassandra designates a list of nodes as the seeds in a cluster. This is critical for a node starting up for the first time. By default, a node remembers other nodes it has gossiped with between subsequent restarts. The seed node designation has no purpose other than bootstrapping the gossip process for new nodes joining a cluster. Thus, seed nodes are not a single point of failure, nor do they have any other special purpose in cluster operations other than the bootstrapping of nodes. Node failure detection. Accurately detecting failures is a hard problem to solve. We cannot say with 100% surety that if a system is genuinely down or is just very slow in responding due to heavy load, network congestion, etc. Mechanisms such as heart beating outputs a Boolean value telling us if the system is alive or not. There is no middle ground. Heart beating uses a fixed timeout, and if there is no heartbeat from a server, the system after the timeout assumes the server has crashed. Here, the value of the timeout is critical. If we keep the timeout short, the system will be able to detect failures quickly, but with many false positives due to slow machines or faulty networks. On the other hand, if we keep the timeout long, the false positives will be reduced, but the system will not perform efficiently for being slow in detecting failures. Cassandra uses an adaptive failure detection mechanism as described by the phi accrual failure detector. This algorithm uses a historical heartbeat information to make the threshold adaptive. A generic accrual failure detector, instead of telling that the server is alive, instead of telling that the server is alive or not, outputs the suspicion level about a server. A higher suspicion level means there is a higher chance that the server is down. Using phi accrual failure detector, if a node does not respond, its suspicion level is increased and could be declared dead later. Using phi accrual failure detector, if a node does not respond, as a node suspicion level increases, the system can gradually decide to stop sending new requests to it. Phi accrual failure detector makes a distributed system efficient as it takes into account fluctuations in the network environment and other intermittent server issues before declaring a system completely dead. Now that we have discussed Cassandra's major components, let's see how Cassandra performs its read and write operations. Cassandra stores data both in memory and on disk to provide high performance and durability. Every write includes a timestamp. The write path involves a lot of components. Here's a summary of its write path. First, each write is appended to a commit log, which is stored on disk. Then, two, it is written to mem table in memory. Three, periodically, mem tables are flushed to SS tables on the disk. Four, periodically, compaction runs the merge SS tables. Commit log. When a node receives a write request, it immediately writes the data to a commit log. The commit log is a write-ahead log and is stored on disk. It is used as a crash recovery mechanism to support Cassandra's durability goals. A write will not be considered successful on the node until it's written to the commit log. This ensures that if a write operation does not make it to the in-memory store, earlier we had discussed the mem table. The mem table is the in-memory store. So just to rewind a bit, a write will not be considered successful on the node until it's written to the commit log. This ensures that if a write operation does not make it to the in-memory store or the mem table, it will still be possible to recover the data. If we shut down the node or it crashes unexpectedly, the commit log can ensure the data is not lost. That's because if the node restarts, the commit log gets replayed. The mem table. After it's written to the commit log, the data is written to a memory resident data structure called the mem table. Each node has a mem table in memory for each Cassandra table. Each mem table contains data for a specific Cassandra table for data not yet flushed to disk. Commit log stores all the writes in sequential order, with each new write appended to the end. Sorry, the commit log stores all the writes in sequential order, with each new write appended to the end, whereas mem table stores the data in sorted order of partition key and clustering columns. After writing data to the commit log and mem table, the node sends an acknowledgement to the coordinator that the data has been successfully written. SS table. When the number of objects stored in the mem table reaches a threshold, the contents of the mem table are flushed to disk in a file called SS table. At this point, a new mem table is created to store subsequent data. This flushing is a non-blocking operation. Multiple mem tables may exist for a single table, one current, and the rest waiting to be flushed. Each SS table contains table data for a specific table. When the mem table is flushed to SS tables, corresponding entries in the commit log are removed. You might be wondering, why are they called SS tables? It stands for sorted string table, and first appeared in Google's Big Table, which is also a storage system. Cassandra borrowed this term, even though it does not store data as strings on the disk. Once a mem table is flushed to disk as an SS table, it is immutable and cannot be changed by the application. If we are not allowed to update SS tables, how do we delete or update a column? In Cassandra, each delete or update is considered a new write operation. We will look into this in detail while discussing tombstones. The current data state of a Cassandra table consists of its mem tables in memory and SS tables on the disk. Therefore, on reads, Cassandra will read both SS tables and mem tables to find data values, as the mem table may contain values that have not yet been flushed to the disk. The mem table works like a write-back cache that Cassandra looks up by key. Generation number is an index number that is incremented every time a new SS table is created for a table and is used to uniquely identify SS tables. So, give me a moment. Um, I think I have some slides in the wrong order. Okay, to boost read performance, Cassandra provides three optional forms of caching. Row cache. The row cache caches frequently read or hot rows. It stores a complete data row, which can be returned directly to the client if requested by a read operation. This can significantly speed up read access for frequently accessed rows at the cost of more memory usage. Key cache. Key cache stores a map of recently read partition keys to their SS table offsets. This facilitates faster read access into SS tables stored on disk and improves the read performance. Key cache takes little memory compared to row cache, where the whole row is stored in memory, and provides a considerable improvement for read operations. Third, chunk cache. Chunk cache is used to store uncompressed chunks of data read from SS table files that are accessed frequently. Reading from a mem table. As we know, the data is stored by the partition key and the clustering columns. Let's take an example. Here we have two partitions of a table with the partition keys 2 and the partition key 5. The clustering columns are the state and city names. When a read request comes in, the node performs a binary search on the partition key to find the required partition and then return the row. So you can also see here from the diagram in 1, we return a row if it's present in the cache. 2, we cache the key for the index. 3, we check the mem table to see if the data is present. 4, we retrieve the data from SS table. And 5, we add the row to the cache if row caching is enabled. I may find my notes for this one. Reading from the SS table. Each SS table has a Bloom filter associated with it, which tells if a particular key is present in it or not. Bloom filters are used to boost the performance of read operations. Bloom filters are very fast, non-deterministic algorithms for testing whether an element is a member of a set. They are non-deterministic because it is possible to get a false positive read from a Bloom filter, but false negative is not possible. I'll say that one more time. They are non-deterministic because it is possible to get a false positive read from a Bloom filter, but false negative is not possible. That means that you can be told that uh, a a value may let me think about for a moment. That means that being a false positive. That means a query to the Bloom filter might indicate that an element is in the set when it is actually not. Bloom filters work by mapping the values in a data set into a bit array and condensing a larger data set into a digest string using a hash function. The digest, by definition, uses a much smaller amount of memory than original data would. The filters are stored in memory and are used to improve performance by reducing the need for disk access on key lookups. Disk access is typically much slower than memory access. So in a way, a Bloom filter is a special kind of key cache. Cassandra maintains a Bloom filter for each SS table. When a query is performed, the Bloom filter is checked first before accessing the disk. Because false negatives are not possible, if the filter indicates that the element does not exist in the set, it certainly does not. But if the filter thinks that the element is in the set, the disk is accessed to make sure. How are SS tables stored on the disk? Each SS table consists of 2 files. And you can see in the diagram, I recommend you take a look. Each SS table consists of 2 files. The data file. And actual data is stored in the data file. It has partitions and rows associated with those partitions. The partitions are in sorted order. Partition index file is stored on the disk. The partition index file stores the sorted partition keys mapped to their SS table offsets. It enables locating a partition exactly in an SS table rather than scanning data. The partition index summary file. Stored in memory, the partition index summary file stores a summary of the partition index file. This is done for performance improvement. For example, if we want to read data for key 12, here are the steps we need to follow. And we're going to see in the figure below, in this figure, in the partition index summary file, we find the key range in which key 12 lies. This will give us the offset 32 into the partition index file. Now, next, number 2, we jump to the offset 32 in the partition index file to search for the offset of key 12. This will give us the offset 3914 into the SS table file. Now we jump to the SS table as at offset 3914 to read the table for key 12. Can you see the order in the diagram here? Where we start with key 12, and this gives us the byte offset in the partition index summary file. Then we jump to offset 32 in the partition index file, search for key 12. This gives us the offset 3914 in the SS table file, and then we jump to that offset to read the actual data itself. As the key cache stores a map of recently read partition keys to their SS table offsets, it is the fastest way to find a required row in the SS table. If data is not present in the mem table, we have to look it up in the SS tables or other data structures such as like partition index. Here's a summary of Cassandra's read operation. First, number 1, Cassandra checks to see if the row is present in the row cache. If it's present, the data is returned and the request ends. 2, if the row is not present in the row cache, Bloom filters are checked. If a Bloom filter indicates that the data is present in an SS table, Cassandra looks for the required data in that SS table. 3, the key cache is checked for the partition key presence. A cache hit provides an offset for the partition in SS table. This offset is then used to retrieve the partition, and the request completes. Cassandra continues to seek the partition in the partition summary and partition index. These structures also provide a partition offset in an SS table, which is then used to retrieve the partition and return. The cache are updated if present with the latest data read. As we have already discussed, SS tables are immutable, which helps Cassandra achieve such high write speeds. Flushing of mem table to SS table is a continuous process. This means we can have a large number of SS tables lying on the disk. While reading, it is tedious to scan all these SS tables. So, to improve the read performance, we need compaction. Compaction on Cassandra refers to the operation of merging multiple related SS tables into a single new one. During compaction, the data in SS tables is merged, the keys are merged, columns are combined, obsolete values are discarded, and a new index is created. On compaction, the merged data is sorted, a new data is created over the sorted data, and this freshly merged, sorted, and indexed data is written to a single new SS table. So, compacting 2 SS tables into 1. Compaction will reduce the number of SS tables to consult and therefore improve read performance. Compaction will also reclaim space taken by obsolete data in SS table. Now, there's a number of different compaction strategies. First, we have the size-tiered compaction strategy. This compaction strategy is suitable for insert-heavy and general workloads. This is the default compaction strategy and is triggered when multiple SS tables of a similar size are present. Second, we have the leveled compaction strategy. This strategy is used to optimize read performance. This strategy groups SS tables into levels, each of which has a fixed size limit, which is 10 times larger than the previous level. Third, we have the time window compaction strategy. This is designed to work on time series data. It compacts SS tables within a configured time window. This strategy is ideal for time series data, which is immutable after a fixed time interval. Sequential writes are the primary reason that writes perform so well in Cassandra. No reads or seeks of any kind are required for writing a value to Cassandra because all writes are append operations. This makes the speed of the disk one key limitation on performance. Compaction is intended to amortize the reorganization of data, but it uses sequential I/O to do so, which makes it efficient. If Cassandra naively inserted values where they ultimately belonged, writing clients would pay for seeks upfront. What are tombstones? An interesting case of Cassandra can be when we delete some data for a node that is down or unreachable. That node could miss a delete. When the node comes back online and a repair occurs, the node could resurrect the data that had been previously deleted by resharing it with other nodes. To prevent deleted neat data from being reintroduced, Cassandra uses a concept called a tombstone. A tombstone is similar to the idea of a soft delete from the relational database world. When we delete data, Cassandra does not delete it right away. Instead, it associates a tombstone with it with a time to expiry. In other words, a tombstone is a marker that is kept to indicate data that has been deleted. When we execute a delete operation, the data is not immediately deleted. Instead, it's treated as an update operation that places a tombstone on the value. Each tombstone has an expiry time associated with it, representing the amount of time that the nodes will wait before removing the data permanently. By default, each tombstone has an expiry of 10 days. The purpose of this delay is to give a node that is unavailable time to recover. If a node is down longer than its value, then it should be treated as failed and replaced. Tombstones are removed as part of compaction. During compaction, any row with an expired tombstone will not be propagated further. Common problems associated with tombstones. Tombstones make Cassandra writes actions efficient because the data is not removed right away when deleted. Instead, it is removed later during compaction. Having said that, tombstones cause the following problems. As a tombstone itself is a record, it takes storage space. Hence, it should be kept in mind that upon deletion, the application will end up increasing the data size instead of shrinking it. Furthermore, if there are a lot of tombstones, the available storage for the application could be substantially reduced. When a table accumulates many tombstones, read queries on that table could become slow and cause serious performance problems like timeouts. This is because we have to read much more data until the actual compaction happens and removes the tombstones. So, in summary, if you stuck it out this far with me to learn how Cassandra works, Cassandra is NoSQL database. It's resilient, peer-to-peer. It features automatic distribution. It's replicated, uses consistent hashing for distributing the data. It's very similar to the big table model. And it has features that are inspired by Dynamo, which is consistent hashing, partitioning, and replication, which if you were here for the session last week, may seem similar. The consistency is tunable, and it uses Gossip Protocol to enable node communication and state sharing. It uses system design patterns such as consistent hashing, quorums, quorums to ensure the data consistency, as each write operation can be configured to be successful only if the data has been written to at least a quorum of replica nodes. Write-ahead log. To ensure durability, whenever a node receives a write request, it immediately writes the data to a commit log, which is a write-ahead log. Segmented log. Cassandra uses the segmented log strategy to split its commit log into multiple smaller files instead of a single larger file for easier operations. As we know, when a node receives a write operation, it immediately writes the data to a commit log. As the commit log grows and reaches its threshold in size, a new commit log is created. Hence, over time, several commit logs could be present, each of which is called a segment. Commit logs segments reduce the number of seeks needed to write the disk. Commit log segments are truncated when Cassandra has flushed corresponding data to SS tables. Commit log segments can be archived, deleted, or recycled once all its data has been flushed to SS tables. As we saw earlier, Cassandra uses the gossip protocol that allows each node to keep track of state information about the other nodes in the cluster. We also talked about the generation number. In Cassandra, each node keeps a generation number which is incremented whenever a node restarts. This generation number is included in gossip messages exchanged between nodes and is used to distinguish the node's current state from its state before a restart. We also discussed the phi accrual failure detector. Cassandra uses an adaptive failure detection mechanism as described by the phi accrual failure detector algorithm. This algorithm, instead of providing a binary output telling if the system is up or down, uses historical heartbeat information to output the suspicion level about a node. A higher suspicion level means there are high chances that the node is down. Bloom filters. In Cassandra, each SS table has a Bloom filter associated with it, which tells if a particular key is present in it or not. Hinted handoff. Cassandra uses hinted handoff to remember the right operation for failing nodes. Read repair. Cassandra uses read repair to push the latest version of the data to nodes with the older versions. Why is Cassandra popular? It's distributed. It's decentralized, so there's no leader-follower paradigm. All nodes are identical and can perform all functions of Cassandra. Cassandra is scalable in the sense of that it can be scaled horizontally by adding more nodes to the cluster without any performance impact, without any manual intervention rebalancing. Cassandra achieves linear scalability and proven fault tolerance on commodity hardware. Highly available means Cassandra is fault tolerant and the data remains available even if one or several nodes or data centers go down. It's fault tolerant and reliable as data is replicated to multiple nodes. The tunable consistency means that it's possible to adjust the trade-off between availability and consistency of data on Cassandra nodes, typically by configuring replication factor and consistency level settings. Durable means Cassandra stores data permanently. Data in Cassandra is eventually consistent as Cassandra favors high availability at the cost of strong consistency. The geographic distribution means Cassandra supports a geographic distribution and efficient data replication across multiple clouds and data centers. To answer your question, for Big Table, we understand that it relies or is used to rely on a GFS to store the actual data. Does Cassandra depend on a particular file system to store the data? No. Cassandra stores its data on disk using its own file format in SS tables, sorted string tables, which are managed within Cassandra's framework. It can run on the various operating systems and environments. even, such as XF4, XFS, NTFS, and other Unix-like systems without requiring a specialized file system. The next question is compaction a non-blocking process in Cassandra? Is compaction a non-blocking process in in Cassandra? So compaction is designed to be a background process, which means it runs alongside other database operations without blocking them. The goal is for compaction to minimize an impact on foreground operations, such as read and writes, to ensure the data remains responsive. So like while it's non-blocking, it's still a resource-intensive process, and so you can use up like a lot of I/O, CPU, disk bandwidth. So for instance, like if there's a heavy compaction process, it might actually be so heavy that it can increase latency for read and write operations. So you can actually throttle this in Cassandra, just an option. Cool. Let's do like a quick quiz. This is like a fun something I wanted to try out here, just to see if folks understand Cassandra. So yeah. So I'm going to say AP, CP, and CA, and then here's the poll. So for those of you here, you're seeing people coming in with votes. Okay. The majority of you guys and girls voted for AP, and that is correct. Cassandra is an available and partition tolerant system. Well done. Next, we have read repair always happens when the consistency level is set to A. Looks like a pretty good number of votes coming in. Majority of folks picked quorum, but the answer is actually all. By quorum, read repair is a consistency mechanism in Cassandra that ensures all replicas for a given piece of data are synchronized during a read operation. When a read request is made with the consistency level of all, Cassandra queries all replicas for requested data. This ensures the client receives the most recent version of the data, as all replicas must respond before the read is considered successful. So the quorum consistency level is when a majority of the replicas must agree, doesn't inherently guarantee that all replicas are contacted during a read operation. Read repair can still occur at consistency levels other than all, including quorum, but it's not guaranteed to happen with every read operation. So with quorum, the goal of it is to strike a balance between availability, consistency, and performance. And since only a subset of replicas are required to agree, it's possible for some replicas to not be involved in a particular read operation, potentially leaving inconsistencies unaddressed until those replicas are contacted by future operations or during empty entropy repair processes. Okay, next. True or false? Nodes can only gossip with specific other nodes in the cluster. Yep, that's correct. You all got it correct. Well done. Next we have true or false. Cassandra automatically assigns tokens to vnodes. Okay, most of you got it right. In Cassandra, when using vnodes, the system does automatically assign tokens to these vnodes. So just to recap, tokens in Cassandra are numerical values that determine how data is distributed across the cluster. Each piece of data is assigned a token based on a hash of its partition key. These tokens define the data ranges for which each node is responsible. When assigning tokens to virtual nodes, vnodes, Cassandra ensures the data is evenly spread across the cluster, optimizing load balancing and system scalability. Awesome. I think, and then I think this is the final one. Sorry, I have to type these out manually. Next time we'll just probably do like 1, 2, 3, 4. What is snitch used for? Okay. Majority of you got it right. There was a lot of answers across the board. A snitch in Apache Cassandra determines the topology of the cluster. It determines each node's rack and data center. So snitch provides Cassandra with necessary information about the topology so it can optimize the request routing and replication strategies to make sure the data is replicated across different physical locations for fault tolerance and reduced latency. And we can actually go back all the way to snitch. I think I don't remember exactly. There we go. Why are we snitching? Since a lot of folks got this one wrong. So here's an example. Let's take an example. Let's assume the client is performing a read with quorum consistency level, and the data is replicated on 5 nodes. To support maximum read speed, Cassandra selects a single replica of the query for the full object and asks for the digest of the data from 2 additional nodes in order to ensure the latest version of the data is returned. The snitch helps identify the fastest replica, and Cassandra asks the replica for the full object. Cool. That concludes this presentation. How are folks feeling about this? Yeah, thank you. Thank you for sticking it out. I know this was pretty heavy. Not surprisingly, a bunch of folks dropped, but if you stuck it through, this I think you'll learn a lot. Yeah, go for it, Kevin.
Hey, so yeah, a few questions. The first one is, it sounds like there's a Bloom filter associated with every SS table. So there's actually like 3 things stored per SS table: the SS table itself, the index, and then also a Bloom filter that I guess is pre-calculated, perhaps.
Yeah. So the Bloom filter is stored of the SS table, and we can look for. There's a really good diagram. So we have the partition index summary. So remember, we have the partition index summary file, and then we have the partition index file. We can find the. Where did I put the partition index file? Oh, I'm having trouble. Yeah, but yeah, it's those 3 things associated. And it was a really good diagram I can't find. Yeah, it is. Log them table.
I think I saw it earlier. Soon. You're almost there. This one, maybe.
Yeah. I thought there was another one with clean filter. But yeah.
So yeah, there's 3 things stored per SS table, essentially.
Yeah.
Okay.
So it checks the Bloom filter first, because checking a Bloom filter is really fast, right?
Yeah.
But the downside of a Bloom filter, you remember earlier where I was like pausing, I was like, it's
yeah, the false positive situation.
False positive situation. Yeah.
Okay.
Yeah.
Okay, got it. My next question is, since we just did DynamoDB and we just did Cassandra today, what are the main differences? It seems like there's quite a few similarities, but it's not immediately clear to me what the differences are.
Sure. That's a really great question. So I think the reason I did both is because they share a lot of underlying concepts that you've seen from both, right? And enables us to do this presentation without going as in depth with some of the things covered in the previous session, which is probably why some people dropped. But you saw, like, we didn't go in depth about consistent hashing. We didn't go into depth about gossip protocol. So these are like core distributed system concepts that are really important to know. But ultimately, just to recap at a high level, DynamoDB is a distributed key value store, right? You can think of it as like kind of like Redis or DynamoDB. So that means that you have 2 API keys, 2 API methods, right? The put or get. That's it. That's all you can do, right? Whereas with Cassandra, which is a columnar NoSQL, if you remember, it's there's a primary key and then there's columns associated with it, right? You can find the table. Yeah, so here, right? You see how we have this partition key and a clustering key? So you can see how there's much more data associated with Cassandra, and it's really great for the way you read data, right? It's has this kind of like linear performance, read-write performance, and it just kind of scales linearly. So you don't have to deal with the kind of the kind of like key distribution problems you have as much. Well, it's a different type of key distribution problem you have to deal with compared to DynamoDB. But if you think about like what a distributed key value store is used for is things for like, trying a good example. Let's say you have like e-commerce store, and you want to look up the um the SKU information for a product, and the the SKU might be the key for it, right? It's going to be super fast to read and write from a distributed KV, right? Whereas with Cassandra, like Cassandra's not actually like you give up on some of that speed in um in reading, because remember, it's not always guaranteed the data is going to be in memory of Cassandra, right? Remember, there's the mem table, there's the um SS table, right? And only mem table is the data in memory. Does that make sense so far? So like Cassandra's really good for like, it's kind of like sequential data, such
Yeah,
as like message history for Messenger.
gotcha. I think I understand. Yeah, the wide column nature is the largest, probably the main difference between the two, it seems like.
Yeah, and
And
there's a little bit of like performance differences. Like it's a pretty big, like it's a pretty drastic performance difference between Dynamo and Cassandra.
okay,
Like
okay.
Cassandra's like can be actually really slow to read sometimes. Uh, so you have to be really, really
Right.
careful about that.
Yes, fast writes because of the append only situation. Okay, gotcha.
Backslash, yeah, of
Yeah. Okay. Did I have another question? Well, I did have a comment at least. So
course.
I recently learned that write-ahead logs are actually pretty much as fast as memory writes, because even though it's writing to disk, because of the way that OS is optimized for pagination and virtual memory. So it's just an interesting tidbit. You're pretty much not sacrificing anything by writing something to disk with a append-only write-ahead log. Um, Alex, are you still there?
Oh yeah, sorry. I did say something. I said was it Kafka uses um uh a write ahead log to be really fast.
Right, right.
Yep. So Ashwin has a question. Go for it.
So I was curious more about the compaction process, and I wanted to kind of get more information on that, as in, like, going through the flow of how reads happen for an existing key, and if compaction is happening as a background process, like, um, how, how does that eventually kind of propagate into um, what what a user would be reading? Like, I wanted to kind of like bridge that gap um, of
I think,
information.
can I try to answer this, Alex?
Sure, go for it.
Yeah, so I think the compaction process in terms of we have the in-memory store, right, where we append new values. It's the in-memory data structure is actually a red-black tree or some balanced tree like that that allows the strings to be sorted. Once it hits a certain threshold, it gets written to an SS table and that threshold is the beginning. The compaction process is, let's say you set some threshold of the number of SS tables that you get with the initial size before you compact them. This would be size tiered compaction strategy. So you would say, okay, I have four of these SS tables now. I'm going to do a merge sort on them across all four of them. And so, yeah, once you merge them, it become a larger SS table. And during this process, you might find duplicate keys across the four SS tables. Let's say your service wrote a bunch of values to the same key or the same row. I'm sorry, row to the same row. Then the latest SS table with the latest value will be kept, I believe, in the compaction process. So this reduces the memory, the storage footprint, and then yeah. So when a read occurs, the SS tables are actually read in sequential order from most recent to latest. And so I'll start with the smaller ones to look for that key. And if they can't find it, then it'll go to the bigger ones that compacted. And then eventually you'll find the actual key that you're looking for. And then it'll take that latest value and return it to the user. I think that answers your question, but let me know if you have more questions.
Got it. So in the merge oh, sorry, go ahead, Alex.
No, go on. No, I was just going to say it depends. That explanation was really great, Kevin. It depends a lot on the compaction strategies that you can see here. But go on, Ashwin. What were you going to say?
So with the merge sort, happening with the SS tables, so okay, that makes sense because they're already sorted, and while that's happening, the tombstones can be skipped from being considered. And are they written into like a new offset completely after sorting, or it's still using like the existing offsets, uh, which don't have a tombstone marker on them?
Sorry, I'm actually not sure I understand the question.
So if we go back to a diagram showing how those offsets look on the disk, yeah, I think this should do it. So now within I think like if within one of those keys, like if they have a couple of tombstones, and I'm assuming something happens to the data file when compaction happens to remove those keys marked with tombstones, right? So does, like, after sorting, is that written to a completely different offset? Sorry, like, um, is it kind of sequentially written into like a different place, or is it using whatever is available in the data file as it is with some changes in there? Not sure if I make sense.
Let me think
Ashwin,
about it. Yeah, go on.
if I understood correctly, Ashwin, my understanding of the process is that it will create a new file and it's just merging the values like you would in merge sort. Like it's just sequentially writing. And my guess would be that it would then, like at the end of it, it would sort of could get rid of the old SS tables that it merged from the source ones, and it would have to like recreate the partition index summary file and the cache files, right? Like that is sort of my understanding. So yeah, I mean they would pretty much be like new offsets because you're merging two files, right? So and again the rationale is there, the sequential writes, like append only writes are like much faster, right? Like and so you want to keep that as a priority.
Right, right. I would assume the same. And so I think, like, with my prior question, like I was more curious about, like, if the background process is kind of like writing to completely new offsets in the data file. How, like, when does, like, it get decided to kind of write those byte offset values to those partition index files, or basically kind of like reverse mapping back to those existing key ranges, and serving requests from the new
So I think this
offsets.
diagram answers your question a bit, right? Where you see compaction over these two SS tables, and we can see that 9, there's a tombstone there, right? And
Mhm.
that doesn't get, then you end up with this consolidated compacted SS table, right? So you want to think of tombstone as like a delete operation, more than anything else, right?
Correct. Yeah, I think that's what I had. Thanks, Alex.
Yep. Cool.
So just to follow up to that, just to the source SS tables in this table 1 and table 2, they would probably get discarded, right? And it would have to generate the newer, like the index files for indexing into this SS table, the compacted one.
Let me think for a moment. So you're asking whether we just discard the old SS table and the other two. So yeah. So like once we compact, the merged data is sorted, and then we'll create a new index over the sorted data, and this freshly merged, sorted, and index data is written to a single new SS table.
Right. Okay. So, and the old ones are garbage collected or something, right?
Actually, not sure exactly what happens, but I know it's discarded somehow.
Okay.
Yeah, I imagine there must be some sort of in memory or on disk file that also has the indexes of all the relevant or like the currently live SS tables. And after that gets updated, then the SS table 1 and SS table 2 can actually be deleted.
Will this recording be available later? Yes. This should be recorded. I don't know how to share it, but I know that the founders do a good job of redistributing it. Overall, how did people feel about this one? I think I took a lot of stuff I thought I made mistakes from the last session, and I improved on it. I think like slowing down and the pacing on this one was much better than the previous one. And I felt like the bullets were a lot better too. That's awesome. Thank you. Yeah, just I think the last one, like I just didn't know how long it would take a Dynamo, and so I was just sort of like, oh my God, I'm gonna run out of time. And then I ended up with too much time. And this one, I got a better sense of how to pace it. Yeah, for sure. Thank you. I learned a lot. Like I just took all the mistakes I noticed from my last session and improved on it for this one.